I'll now try to describe how one would arrive at the subproblem. A discussion of this type is clearly clumsy because I'm trying to describe a thought process, and it's not necessarily useful for everyone. For some people, it's useful to just look at the final answer and try to think about how one would come up with it. For some people, it's good to go through the thought process. I'll leave the choice up to you, but if you feel like the thought how to arrive at the subproblem is a clumsy discussion, feel free to skip ahead to the final um, description of the subproblem, which I will mark using a slide. Feel free to skip ahead in the video to that point. All right, so now we will try to arrive at a subproblem uh, for this problem of dividing the polygon into triangles with of such that the entire triangulation of minimum cost. So the typical thumb rule that I use is to imagine an optimal solution and try to break up the optimal solution into smaller pieces that are also optimal. So for instance, over here, this is some polygon, and I don't know how the optimal solution looks like, but let's imagine the optimal solution and suppose it looks like so. So how would one break up this optimal solution? Well, one would just, for the first attempt, one would just try to break it up along one of the cuts that we make, along one of the diagonals. So let's just say that, we break the optimal solution along the 1, 6 diagonal. Right? So now, if I look at the left half and the right half, of course, because it's the minimum cost triangulation, you'd have the minimum cost triangulation of the left half and the right half. So it is a valid thing to say the minimum cost triangulation of um, the minimum cost triangulation of the entire polygon that we had earlier, which is this, let me just call the polygon 1, 2, 3, 4, 5, 6, 7, 8, is of course equal to the minimum cost triangulation of the left half 1, 2, 6 plus the minimum cost triangulation of the right half, which is 6, 7, 8, 1. So depending on assuming 1, 6 is part of a minimum cost triangulation. Assuming this you're looking at an optimal triangulation, if you look at a diagonal there, of course the two halves are going to be optimal. So this suggests that you could just try to break the polygon along these cuts, which is a reasonable thing. But what fails here is as you break it up using arbitrary cuts, you will end up getting pieces that are too numerous, as in you'll get all sorts of different polygons. For example, let's say I cut it this way, then I use some cut here, and then maybe some other cut here, and then I end up with a cut here. So I'm ending up with, at some point I'll be talking about the minimum cost triangulation of this piece, which is 1, 3, 5, 6, and I'd be asking what is the minimum cost triangulation of 1, 3, 5, 6. In general, in this polygon, since you don't know what the optimal cost triangulation is, as you try many different cuts, you'll end up trying to solve subproblems which correspond to every possible subset of the 8 vertices. Specifically, if I look at any subset of these 8 vertices, for instance, let's say I look at 1, 3, 5, 6, 7. Okay, so this is a particular subset of these 8 vertices. They form some polygon. So 1, 3, 5, 6, 7, 1. So they form this polygon, and you would be looking at all possible such polygons, and you would be wondering about what is the minimum cost triangulation of that in the dynamic programming algorithm. This is because we are making cuts in an arbitrary fashion, and in particular we'll end up, as we make all possible cuts, we'll end up with all possible pieces as subproblems, and every subset of the n vertices corresponds to some piece that you could get, and input you would end up trying to solve 2 to the n different subproblems corresponding to every piece. So what it suggests to us is, as we look at the optimal solution and break it up into subproblems, we want to do that in an orderly fashion so that the pieces that we get are not completely arbitrary but polygons of a specific type. In particular, one would want the number of different kinds of pieces that you get as you make these cuts to be few in number. You don't want 2 to the n different kinds of pieces that you could arrive at as you make the cuts, but fewer, let's say n squared polygons or n cube polygons or so on, so forth. So our goal now is to break up the optimal solution in a way so that each of the pieces that we get as we break it up are actually coming from a small number of different polygons. One would hope that if you break up the solution in a very orderly fashion, you can arrive at pieces that are also fairly simple. For one very simple kind of a polygon that you could expect is a section. A section is a part of the polygon that you get by doing the following. Suppose you start at a vertex 2 and you start following the polygon in clockwise direction for a few vertices, and let's say 2, 3, 4, 5, 6, and then you return back to the starting point, and that is a section. So let me just write down what a section is. A section is given by start point, vertex I, no, but we'll use the word, and vertex J. The section between I and J is basically you walk clockwise from I to J, and then once you reach J, you jump back to I. So the section here, this is section 2,6, and on the other hand, if you looked at the section 6,2, that would be given by the following. You would have to walk clockwise from 6 to 2 and then return back to 6, and that would be section 6.2. One piece of notation which will be useful for us later is to call the edges that we traverse along the polygon to be the polygon edges, and the final jump back to the original vertex to be the jump edge. So in particular, this edge 6.2 is a jump edge, and in the section 2.6. So each section has precisely one jump edge. Now we're ready to formally describe the subproblem. Before that, let me just recall some notation. Recall that the vertices are given by v1 through vn. These are the vertices in clockwise order around the polygon. Vertices of the polygon in clockwise order. And we can define the section of I to j to be the convex polygon formed by just walking from the vertex vi to vj and then jumping back to vi. So basically it's the convex polygon formed by vi plus 1 up to vj and then vi. So it's a sub-polygon of the original polygon. And as you can see, there are roughly n squared sections. And so now we are ready to describe the subproblem. Essentially, our subproblem, I'll use the notation T, Tij would be the cost of the minimum triangulation, or the value of the minimum cost triangulation of the section Ij. Okay. note that if we look at the section 1n, that's essentially the original polygon. So our final answer that we're looking for is T1, n.